Now, in continuation to my previous class, I was dealing with the nonlinear programming problem with inequality constraints. I just introduced the how we are getting the KKT first order necessary conditions, but I did not say about the equations etc. Today I will talk on that. Now, if I just start my class with again with the same general minimization problems, nonlinear programming problem, where there are m number of constraints which are of less than inequality type, and we are introducing the slack variables. Slack variables are non-negative slack variables as Sj. Now, we will deduce the Kuntakar condition, necessary condition for this type of problem. Now, this why we say this is the KKT condition, there is a big history to it. In 1951, Kuhn and Tucker, these are two scientists, they only developed the first order necessary condition, and they declared that these conditions are, when these conditions are sufficient as well for nonlinear programming problem. That was invented in 1951, and since then it was being named as the Kuhn-Tucker condition. But after few years it has been seen that there was another person by the name of Karush. He already did in his master's thesis the work already in 1939. That is why since then people are calling it as a Karush-Kuhn-Tucker condition. These are the names of three persons, Karush, Kuhn and Tucker, and few people are still say Kuhn-Tucker condition, both are same. You can name it as either KKT condition or KT condition, but we prefer the name KKT condition. Okay, and this is the necessary condition, but there is certain properties are there for this necessary, for the nonlinear programming problem, when this necessary condition will become the sufficient condition to get the global optimality. Now, there are before going into detail about the KKT condition, I will explain few problems to you. Okay, let me start with the first problem. This is one nonlinear programming problem, minimization of x square plus y square subject to y minus x minus 2 less than is equal to 0, and another one x square minus y minus 4 less than is equal to 0. Now, as I showed you in the last class, we can get the Lagrange function from here by introducing the slack variable. After introducing the slack variable, both the inequations will become the equation. Then after attaching the KKT multipliers instead of Lagrange multiplier, because as I said, KKT condition, the process is the extension of the Lagrange multiplier process, Lagrange theorem rather, we can do it. But let us try to understand what is the geographical picture of this problem. Now, the first one is the line, there is no doubt about it. Let me draw the line with the green, y minus x minus 2, that is why I can say this is the line for us. Okay. What is the next? Next constraint is x square minus y minus 4 is equal to 0. That means it is a parabola. The parabola, if I just draw again the parabola will be like this. This is the line, this is the parabola. Okay. Now, what is the objective function? Both are less than type, that is why we can say that this is my feasible space. Okay. Now, what is the objective function? Objective function is minimization of x square plus y square. Now, within the feasible space, if we just look at the feasible space, you can very easily find out the optimal solution is only one, that is 0 0. because there only the objective functional value is minimum. That is why your optimal solution will come at this point. Now, this is different from the example I explained you in the last class, where we have considered the constraint as the ellipse and the objective function as a circle, but in the ellipse we considered the sign as equality type. That is why the feasible space was only the boundary of the ellipse. But here we are considering the space where we are considering the inequality constraints less than is equal to 0 both the cases. That is why we are having the feasible space is this whole feasible space, this one the feasible space together. And here if you just find out the objective functional value, very easily we can say that it is the minimum value of the objective function. But if you ask what is the maximum value of objective function, then we can say something else. But if we consider the problem as a minimization problem, what we could see that? We could see that both the constraints are inactive constraints. That means both the constraints are not contributing anything to the optimal solution. In other way, we can say that if we just change the constraint, if we just tighten the constraint or if we relax the constraint, it will not affect the optimal solution as well at all. But the question comes, if these constraints are not contributing anything to the optimal solution for this minimization problem, but if we consider the maximization problem, the situation is different, because the circle will go further and further, probably at this space or somewhere we will get the solution. My figure is not symmetric, that is why it is not giving you the exact solution. If you want, you can find out the maximum value for this objective function. In that case, you can say that both the constraints or either of these two constraints are contributing on the optimal solution. But once we are considering the minimization problem, nothing, no constraint is contributing, then the question comes, why we will carry both the constraints farther and farther for our calculation? Can we not drop? Okay, this is a question comes to your mind, because unnecessary, if we do the unnecessary condition this and that, it will take unnecessary longer process. That is a bigger question comes in our mind. Now, let me consider another problem for you. Minimization of x square plus y square subject to x less than is equal to 10 and x minus y square minus 4 less than is equal to 0. If this is, if we just draw the graph of it, what we could see that x less than is equal to 10, if it is 10 for us, x less than is equal to 10, alright, this side, and y square is equal to x plus 4, that means it is a parabola. Again the parabola will be, if we just draw it, x is equal to 10, this is 0 0, then the parabola will be this one, alright, because we are having y square is equal to x plus 4 and y equal to 10, and both are of less than type, less than equal to type, then we can say this is my feasible space, alright. Now, we are considering the minimization of x square plus y square. This is my objective function. That is why again the circle center is 0 0, it is going further. Then where will be the optimal solution? Optimal solution will come here. Again you can ask that if the constraint y equal to, this is x equal to, this is x equal to 10. If x equal to 10 is not contributing anything to the optimal solution, why we really will carry this constraint at all? This is the inactive constraint, is it not? Now, the last problem let me consider for you, that is minimization of x square plus y square. I am leaving to you, you find out which one is the inactive constraint and which are the active constraints or all are active for this problem. Minus 3y minus x less than equal to 0. You need to find out which are the active constraint, which are the inactive constraint. Now, that is the question given to you. Okay. Now, this is one part, but then there is a big question in front of us in nonlinear programming problem. Now, KKT condition is such a condition. Through the necessary condition, we very easily we can find out which one is the active constraint and which are the inactive constraint very easily. And there are a few features for the KKT condition, that since this is the necessary condition, that is why the whatever bonds we are getting through the KKT conditions, these bonds are being named as the KKT point, and there are few more properties of the KKT point. All the KKT point will be either a local minimum or local maximum. Okay. And KKT points must be regular. That means regular means this must satisfy all the constraints. Not only that, the gradient of the constraints at the KKT points must be linearly independent, then only. This is the property of the KKT condition, that the KKT points are regular. And if we consider the unconstrained problem, just I showed you the first problem. First problem can be treated as an unconstrained problem where there is no constraint at all, because constraints are not contributing anything. That is why there is no, we can say that all the inequalities are inactive. And if we have the inequality constraints, few inequality constraints which are active and few inequality constraints which are inactive, through the KKT condition we can very easily can find out for the inactive constraints, then the KKT multiplier is 0, and for the active constraints KKT multiplier will be non-zero. That is the symptom will be given through the KKT condition. That is why let me just go through the KKT condition in detail. This is the Lagrange function. When we have m number of constraints with us, all are of less than type, and we are introducing m number of slack variables there, then L can be of type fx plus this way. Okay. Now, let us deduce the necessary condition. How many variables you are having? You are having n number of decision variables, you are having m number of KKT multipliers, these are all lambda j's. We are having m number of slack variables which are non-negative, and the constants, these are the constant. That is why we are having 2m plus n number of variables now. Therefore, we can in the first order condition we will have 2m plus n number of equations. The first equation would be by considering the first order derivative with respect to xi. There are n number of xi's because we are considering the in the n dimensional space. That is why very easily from here we can write it. There is no confusion about it. What about the next? That if we consider with respect to lambda j, because lambda j's are varying, we do not know whether lambda j is positive or negative or 0, that could be anything. We need to find out the values for this. That is why these are the variables. With respect to these variables, if we just equate to 0, then we will get the original constraint. From here we can write that gjx must be less than is equal to bj, there is no problem at all. And then is another constraint, that is del L by del Si is equal to 0, because we are having the slack variables here. And from here if we just do, we are getting 2 into lambda j into Sj is equal to 0. Okay. This is being named as the feasibility condition, this set n number of equations. These m number of equations are being named as the These are the optimality conditions, this is the feasibility condition, and this is about the complementary slackness condition. I will tell detail about it, but before to that I want to say few things to you, just to see. We are getting the condition that lambda j Sj is equal to 0. I can just remove 2 from here, there is no problem at all, and we are getting Gjx plus S square Sj square is equal to Bj. We are getting both the equations together. Alright. What exactly we can say from the first equation? That lambda j can be j is equal to 0, it can be. Other option is that lambda j not is equal to 0. If lambda j is equal to 0, what exactly we are getting that Sj is not equal to 0, one option. What is the meaning of it? It means that from this equation, if Sj is not equal to 0, then we can get that Gjx is strictly less than Bj. Alright. What does it mean? It means that this constraint is inactive constraint at this stage, because it is not being satisfied with the equality type. Just see the other way. If lambda j not is equal to 0, then xj is equal to 0. Then what exactly we are getting? If xj is equal to 0, we are getting from here Gjx is equal to Bj. That is why in this condition we are getting these are all the active constraints. Alright. That is why from here you can say, you can conclude very easily for lambda j is equal to 0, corresponding constraint must be inactive, and when lambda j not is equal to 0, corresponding constraint must be active. But whether lambda j is positive or lambda j is negative, that depends whether we are considering the minimization problem or the maximization problem. The physical significance of lambda j already I explained to you in the last class, but still I will say once more about the sign of lambda j for the minimization and for maximization both. Alright. Now again this is a necessary condition we can say, and we are having how many number of unknowns? We are having 2m plus n number of unknowns and 2m plus n number of equations, but we can get the solution for it. This is the optimality condition, this is the feasibility condition, and the complementary slackness condition says us many things. Now there are few properties of lambda j. I will discuss this part later on. This is for that was for the minimization, and at least we can say that lambda j is non-zero value. Okay. If we consider the less than type, we will see, if you remember I told you if lambda j is positive, then for minimization problem this must be less than is equal to. Okay. That is why we said all this thing I will detail, and this is the reverse case for maximization problem. Now let us consider one example from here. Before explaining the example, I will talk few properties of this geometrical interpretation of this Lagrange multiplier. Okay. We are considering, for explaining this thing, we will consider three constraints. One is G1 less than is equal to 0, G2 less than is equal to 0, G3 less than is equal to 0. Three constraints we will consider, and we will explain what is the meaning of, and we have the objective function minimization of f. Let this is my G1 equal to 0, this is my G2 is equal to 0, and this is my G3 is equal to 0. This is my G3 is equal to 0. Now say This is the objective function for us. This objective function is moving. Now, G1 less than is equal to 0, G2 less than is equal to 0, G3 less than equal to 0 gives you this space. Okay. This is the convex space. Now, if the objective function, if this is the level curves of the objective function, you could understand that here we will get the minimum value of f. What we can say here, see, this is the gradient direction of f, is it not? Because objective functional value is increasing this way. That is why we can say that this is the direction of grad f at this optimal point. This is my optimal point x star. Okay. What else we can say? At this point, the gradient of G1 would be where? The gradient of G1 would be this one, alright, and gradient of G2 would be this two, because these are all the, at the optimal point, if we just consider the tangent, then gradient would be the normal to that tangent. That is why grad G1 and grad G2 would be this way. If I just extend it further, this is minus grad G1 and this is minus grad G2. Okay. What you can say? One thing we can say that if we consider any direct from this point through the feasible space, I can move in different direction, is it not? Let me consider one of the direction as this one, which can be named as the feasible direction. There is a nice property of this feasible direction I will discuss in later classes, but I can say from here S is the feasible direction, because if I move through this direction, I will be still in the feasible space. I can move further and further. Once I am coming here, this is not the feasible direction. That could be the feasible direction. That could be the feasible direction. This could be the feasible direction. But from here, at least if we say that this is the feasible direction, S is the feasible direction, alright. Now, here up to this graphical, now I am coming to the which part? I am coming to the KKT condition. What is my KKT condition? Grad f plus lambda 1 grad G1 plus lambda 2 grad G2 plus lambda 3 plus grad into grad G3 is equal to 0. This is the optimality condition we got from the first equation. Now, what if this is for the minimization problem, if this is the optimal solution, then lambda 3 must be 0, because this is inactive constraint, G3 is inactive here. That is why this term will go out. What exactly we are getting from here? We are getting grad f is equal to minus lambda 1 grad G1 minus lambda 2 grad G2 into grad G2. There is no problem, but just if I just see here, what exactly we could see that grad f can be represented in terms of combination of two grad G1 and grad G2 and with the minus sign. That is quite acceptable to you. What else you can say? You can say that if S is the feasible direction here, if grad G1 is this side and grad G2 is this side, then we can say S is making acute angle with grad f. Since it is making acute angle with grad f, these are all vectors. If we just take the dot product of it, then we can say grad f, rather ST dot grad f. ST means that is the transpose of S, dot grad f must be greater than 0, because it is making the acute angle. What else we are getting? We are getting from here that ST dot grad G1, and what you can say about it? Grad G2. S is making acute angle with grad F, S is making acute angle with minus grad G1, S is making acute angle with minus grad G2. But on the other hand, S is making obtuse angle with grad G1. Similarly with grad G2, that is why both are coming negative. That is very much reflected from this equation, because if we just pre-multiply with S, this one ST, this is equal to minus lambda 1 ST grad G1 minus lambda 2 ST grad G2. Clear? That is very much reflected here. And what is the necessity for us? The necessity is that lambda 1 and lambda 2 both must be greater than equal to 0, because these conditions are holding because of this only. Alright. That is why from here what we can conclude that if we consider S as a feasible direction, in the feasible direction S, if it is so, then S into the gradient of the objective function is greater than 0, S into means dot product, inner product I am considering, grad of G1 is less than 0, S inner product with grad of G2 is less than 0. Since we are considering the minimization problem, then can we conclude that lambda 1, lambda 2 greater than equal to 0 from this condition? Think about it. Okay? That is why, as I said before, that for the minimization problem, there was a condition that if G1 is less than is equal to 0, we have considered that the KKT multipliers must be, if I just go back to that page, just to see, oh sorry, look at this. If we consider the constraints of the type Gj less than is equal to Bj, then we can conclude that all the KKT multipliers must be positive. And if we just extend this geographical interpretation with the constraint Gj greater than equal to Bj, then we can prove that the KKT multipliers are always less than is equal to 0. That is the task I am giving to you. For the set of constraints, try graphically and geometrically try to prove that lambda j always will be negative for the type Gj greater than equal to Bj. Similarly, for the maximization problem, the case is reverse. If we consider, here also we can explain, because if the function is moving further and further, we can find out the optimal solution here, is it not? We can see the optimal solution will come here, because the objective function is moving this way. These are the level curves of the objective functions. Okay. This is the optimal solution. Just try to prove for less than equal to type always lambda j would be lesser than equal to 0. Equal to 0 we are including because few constraints are the inactive constraints. For the inactive constraints always the lambda j equal to 0, and for the active constraints only lambda j is non-zero. That is why try to prove that for maximization problem we will get, once we are considering the set of constraints as G1 less than is equal to 0, G2 less than is equal to 0, etc., then you have to prove that lambda, the KKT multipliers must be non-positive. Similarly, for the constraints of the type Gj greater than equal to Bj, the KKT multipliers must be non-negative. Okay. With that, today I am concluding my class. In the next, we will solve few problems on KKT conditions. Thank you very much.